Welcome, everyone. We just heard an excellent ITC colloquium by Matt Kunz, who's sitting over there, and can tell you anything you wanted to know about plasma physics, astrophysics. So if you have a question that is nagging you about plasmas in astrophysics, go speak with Matt. Well, you will tell them if you don't know the answer, right?
Yeah.
That's a fair answer. We have, as usual, 4 speakers today. We'll start with Sara Issaoun. She's from here, and she will tell us about the size, shape, and scattering of Sagittarius A star at 86 gigahertz, the first VLBI with ALMA. And Sara is also at the Black Hole Initiative. No. Matt will follow her and tell us about waves just aimed what they used to be, or how to make yourself heard in a collisionless plasma. We look forward to that. How to make waves great again. And then we'll hear from Gerry Gilmore, visiting us from the other traditional Cambridge. Is Gerry here? Oh, great. And he will tell us about testing non-Einsteinian general relativity by astrometric gravitational wave detection. Presumably with guys. And finally we'll hear from Rana Ezzedine from MIT. She will tell us about precise chemical abundances of the most iron-poor stellar relics of the early universe. And I should mention that Gerry is giving the CFA colloquium later in the fall. So anyone interested is welcome.
Thank you. So my name is Sara. I'm a graduate student at Radboud University, and I'm visiting for a few months Issaoun and the BHI. And I'll be talking to you today about observations of Sagittarius A star at 86 gigahertz taken in April 2017. Which is the first VLBI campaign with ALMA as a phased array VLBI station. So the supermassive black hole Sagittarius A star, I assume you're all familiar with, it causes these elliptical orbits in the S stars in the galactic center. It has a mass of about 4 million solar masses, and it's at a distance of about 8.1 kiloparsecs to us. So one of the main questions to learn about supermassive black holes and what do they look like, and Sagittarius A star is the best target to learn about them because it's the closest to us. And they're observations of what we call proto-event horizon telescope that set the size of the shadow of Sagittarius A star to be about 50 microarc seconds, which is about 5 Schwarzschild radii. To put that into perspective, this little arrow here is about 10,000 Schwarzschild radii, so we're really peering right into where the star is here. Of course, there's a long-standing historical debate about the nature of the radio emission in Sagittarius A star. What is the emission process that actually dominates the radio emission? Is it predominantly an accretion disk, or is it a jet or an outflow? So you've all heard of the Event Horizon Telescope. It's a global VLBI array that's operating at 1.3 millimeters. The goal of it is to observe Sagittarius A star and another black hole M87, and it now has ALMA as of 2017, and this was work done by the ALMA phasing project led by Shep Dolman to equip ALMA for VLBI. And in 2017, ALMA joined the EHT at 1.3 millimeters, and the APP was also extended to 3.5 millimeters to the global millimeter VLBI array. In 2017, 40 antennas were phased up as part of ALMA, creating a kind of mega dish with extreme sensitivity in the Atacama Desert. So on top of the increase in sensitivity, it gave valuable north-south baselines to both the EHT and the GMVA. So of course, since we don't know what the radio emission of Sagittarius A star is, we try to look at 1.3 millimeters, but unfortunately, because of GR, the shadow is what is the dominating feature in 1.3 millimeter images. So here's an accretion disk dominated and a jet dominated model. So here, these are in linear scale. The jet would actually be more visible if we look in log scale. It is there, just really, really faint. And so for EHT, we wouldn't be able to really see a difference between these two. They would both be dominated by the size and shape of the shadow. So we have to zoom out a little bit to try to see the accretion flow. And at 3.5 millimeters, we can start to see differences in the accretion flow between the disk-dominated model, which kind of looks more symmetrical and spherical, and the jet-dominated model, which is more elongated. Now, unfortunately, because we're peering through the galaxy, we're actually subject to interstellar scattering. So these are what the models actually look like with the interstellar scattering. You can't really tell which is which. And then, unfortunately, as you go to longer and longer wavelengths, although you would expect the disk or jet emission to be more visible, you're also subject to stronger interstellar scattering that goes as lambda squared. And what the scattering does at longer wavelengths is basically stretches the source predominantly in the east-west direction. So it becomes more and more difficult to disentangle the stretching from the scattering and what the actual intrinsic structure behind the scattering looks like. So at 3.5 millimeters, we hit this soft spot where the accretion flow is still dominating the emission, and you can start to disentangle the scattering effects from the intrinsic structure. So there's actually more to worry about. So although this blurring effect or stretching effect isn't so dominant at EHT wavelengths, we start to deal with what is called refractive noise that causes these wiggles and distortions in the image. And depending on the scattering theory, interstellar scattering may actually contaminate the tests of GR we plan to do with the Event Horizon Telescope images. Here's a nice example done by Zoe Zhu, a graduate student here at Harvard. She takes this nice, smooth, unscattered ring, and she scatters it with the two models at 1.3 millimeters. Both of these scattering models actually fit observational constraints to date. This is decades of monitoring at longer wavelengths, and they both create this blurring effect that we see in observations. But at 1.3 millimeters, they look very different. This J18 model has basically the same blurring of the ring as the GSO6 model, but they have different levels of refractive noise. The J18 model has this low level of refractive noise that creates small ripples, but you can still be able to see the ring pretty clearly. The GSO6 model has a very strong level of refractive noise, which creates very strong distortions and would be pretty disastrous for EHT. So the difference here is that the short baselines would actually see the same thing for a 3 millimeter or 1 millimeter, but the long baselines would actually see different levels of flux. So here, the long baselines would see a lower flux than what we would expect from this one. So our observations with ALMA and the GMVA consistent of these stations in April 2017. We have the VLBI stations in the US, the GBT Green Bank telescope in Virginia. We have the Yebes and IRAM 30-meter telescopes in Spain, Effelsberg telescope in Germany, and ALMA joining us in 2017 with 40 phased-up antennas. So here's our correlated flux density as a function of baseline length. So over here are our short baselines with the VLBA and the GBT. These short baselines have been previously observed in past experiments, and everything past this gray line here are detections to ALMA, which are brand new to our data set. What's interesting here is that previous experiments have fitted a Gaussian to these types of measurements, and the major axis and minor axis of that Gaussian fit are plotted here in dark blue. What's interesting about our data is that our ALMA GBT baseline, which is our most sensitive baseline, we reach SNR of about 200 on this baseline, is actually slightly higher than what we would expect if the Gaussian model from previous experiments was valid. So it turns out that we're seeing a little bit more flux than what we would expect from the minor axis of the source, which means that the scattered source actually has a slower fall off than what we would expect from a purely Gaussian morphology. Another interesting thing from ALMA detections is that long baselines to ALMA here with the VLBA reveal a low level of refractive noise. So remember I told you there's this stretching that happens with these two models that would basically make these ones look the same, the short baselines, and then the long baselines would show different levels of flux. So this is the flux level that the J18 model predicts at 3 millimeters, and this is the flux level that the GSO6 model predicts at 3 millimeters. So we end up with something actually a lot lower than what the GS06 model predicts. This is really encouraging because our new ALMA detections are able to rule out the GS06 scattering model, and this is really encouraging for EHT science. We don't have to deal with this terrifying model for Sagittarius A star images. Now we move on to the next step. We understand the scattering properties of our image. Now we try to reconstruct an unscattered image. So how we do that is basically similar to adaptive optics, but we can do it in post-processing by separating the two effects of the scattering screen. So here's a simple GRMHD simulation, and then this is what happens with this diffractive blurring that stretches it mostly in the east-west over here, and then the refractive noise that creates these small ripples in the image. So here's the image we actually obtained for Sagittarius A star. This is our scattered image, which is basically this east-west stretched image that looks fairly Gaussian-like, which is pretty consistent with past observations. What's interesting, though, is that we reconstructed an unscattered image that looks fairly symmetrical. And it has a size of about 120 by 100 microarc seconds, which means that the emission at 86 gigahertz originates within about 12 Schwarzschild radii of the black hole. The shape of it is also really interesting. We basically reconstructed example images of jet and disk-dominated GRMHD models using the same imaging techniques that we used on our data set. So we basically sampled these GRMHD models and created reconstructed unscattered images. So here's the image we got on our data for comparison, and we compare it to a disk model that is basically 60 degrees inclination, which looks fairly symmetrical, and a jet model that is face-on, so you're looking almost right through the jet nozzle, which looks also fairly symmetrical. And then these two are two jet models with different accelerated electron prescriptions that are 90 degrees inclination that look fairly elongated. So it turns out that jet models actually appear too elongated unless they're nearly face-on, that they look like this one. And disk models actually match our image without any fine-tuning of the simulations to match 3 millimeter sizes. So this is really interesting because persistent jets are ruled out by our image of the intrinsic source. So in summary, first VLBI with ALMA was a huge success at 3 millimeters, and this gives, I guess, an encouraging outlook to what we can expect from the Event Horizon Telescope for Sagittarius A star. We found that the size of Sagittarius A star at 86 gigahertz is about 12 Schwarzschild radii, and that the shape is highly symmetrical, and that jet models do not fit 3 millimeter observations unless they're face-on. And the scattering of Sagittarius A star enables us to rule out the GS06 model because it predicts too high flux than what we see on ALMA baselines, and the J18 model is consistent with our measurements. Thank you. That's right.
So the fact that we don't see a jet at large scales means that there is no jet. Why would anyone think that there is a jet? I must be missing something.
So I need to be careful here. But there are actually several models that predict an intermittent jet. So there have been studies of these time lags where you see a kind of lag in frequency of Sagittarius star light curves that may predict that there is some outflow that actually makes it basically that the high frequency light curves arrive earlier than low frequency. And there are other studies that say that perhaps the jet is actually hiding along the scattering major axis. And so if you deconvolve with a Gaussian that would be stretched in the east-west and your jet is in the east-west, you wouldn't be really able to see it unless you have really high dynamic range. And the sensitivity of our experiments is a little bit impaired in the east-west direction. So I think there's still more work to be done to really be able to rule out at least intermittent outflows or jets. But persistent jets, I guess, are not seen yet.
Just to follow up on Avi's question, this may be totally naive, but wouldn't it be extremely weird to have the jet be face on? I mean, wouldn't I expect it to point out of the galactic disk like the Tommy model?
I guess that's true. I think if you take into account the the rotation of the galactic, or the orientation of the galactic plane, you would expect the jet to be basically perpendicular. But as you go in the inner scale, I guess if it's a small jet, it could go in any direction because the inflow of material can go in different directions on the black hole. The large scale may be kind of disk-like, but the closer might be a little bit more turbulent or kind of quasi-spherical accretion and different. There are different models that could predict different jet orientations.
Sara mentions that the gas is most likely to originate from the circumnuclear ring around the center. And in fact, there are some estimates of the speed being the black hole being perpendicular to that. So it's not the galactic plane, it's more the supply of gas from the vicinity.
But that could also be tilted to a different scenario.
Yep.
Do these data set any limit on the accretion rate of material?
I don't think so. I think we haven't explored that. Yeah.
Yes. Continuing on this point of the galactic disk and the internuclear ring. So can you from the image constrain if there's a disk, what is the orientation of the disk? Is it like aligned with the galactic disk, or maybe is there some tilt? If it is a disk at all, or something more spherical?
So we did study only a very small sample of GRMHD simulations. We tried disk models with different inclinations, and they all seem to fit our size and asymmetry constraints because we still have pretty large error bars for our constraints. So we're not able to give very tight estimates on what the inclination of the disk models would be. But for the jet models, it's really easy to see that they would actually show very large asymmetry if they're actually at high inclination. And so for that, we're able to firmly rule them out.
I was just curious if any of the stars around the Sagittarius A star are also radio stars, and whether they could be observed with the same technique, the same data, to determine the orbits and interaction, maybe even see interactions between the various stars.
So the S stars are the closest stars to Sagittarius A star, and they're pretty far away from what we're looking at now. I think I showed you this one. So these stars are the closest to the black hole, and the S2 star is the one that comes, I think, 1,000 AU distance to the black hole at the smallest distance, which just happened in June, and that's how the gravity team got these amazing measurements for Sagittarius A star. So the size of this arrow is 10,000 Schwarzschild radii, and our radio size is 15. And so we're really looking way past any stars that we could see in the radio. And these ones can be seen in the infrared. There are a few, I think, evolved stars that are further out that have maser emission that may be observed to be able to determine some gas dynamics near the black hole, but they're still much further away from these ones.
But the key point to keep in mind is that S2 is passing within about 1,000 Schwarzschild radii, and once you get to 100 Schwarzschild radii, the star will get disrupted by tidal forces. So you cannot have stars closer than 10 times closer than S2.
Yeah.
Okay. One last thing, Sara.
I'm being recorded, huh?
No pressure.
Yeah, right. Great. So I've picked something which is a very clean bit of plasma physics with wide-ranging applications, but it's also indicative of, or sort of representative of a lot of things that are going on right now in my research. But it's nice because it's just a single wave and it's something very simple. So it should fit in the 10 minutes. So let's just do a very simple thought experiment. So just consider a small amplitude sound wave. Simple enough. If you consider the sound wave propagating through a weakly collisional magnetized plasma, or even just like an MHD plasma, the dispersion relation for that wave is really simple. Right. So its frequency is just its wave number times some sound speed. If there's any viscosity, there might be some viscous losses to the sound wave. And except for steepening sound waves, they just propagate just fine in MHD or Brzezinski MHD or hydrodynamic fluid with viscosity. We know that in a collisionless plasma, this is not true because of Landau damping. Basically, you don't need to know what these symbols are. The only important part is that the damping rate of such a sound wave in a collisionless plasma is something like 1 times its propagation frequency. So in one wave period, that wave will exponentially decay. And this is because of Landau damping. Basically, you send in a wave, and there's some part of the distribution function of the particles which can ride the electrostatic potential in this wave and just leach energy out of the wave and damp the wave because of that. So Alex Shekachikhin was my first postdoc advisor, had this quote in his lecture notes that in a collisionless hot plasma, no one will hear you scream because you yell and it just Landau damps in one wave period and nobody can hear you. So the punchline of this talk is just no one will hear you whisper, but if you scream, people will hear you. So it's reassuring if you find yourself around a black hole or something. Right. And the reason for this requires just one slide of prerequisite material, which is just in a magnetized plasma, there's invariance in the system, and these invariants just come from the magnetic field introducing periodic motion. And without getting into anything, I've just sketched these visually. So here's a magnetic field gyrating around some field lines, and if I decrease the field, the velocity of this particle adjusts, so it's always encircling the same amount of flux. There's something called a bounce invariant, which is if I take a magnetic mirror like that and I have some particle just bouncing back and forth inside of this potential, and if I just change that potential a little bit, the velocity of the particle changes. You can think about this also in the context of just a pendulum whose length slowly changes, and asking how does the frequency of this pendulum change if I change the length slowly. It's an adiabatic process. The important part for what I'm going to say is that if you average these over all particles, this says something about how the pressure tensor of the gas evolves. So like if you change the density or the magnetic field strength in various ways, the distribution function of the particles has to adjust because of these kinds of constraints. And so I'm going to show you what this does to just a simple wave after this slide. This is just another visual just to hammer home this prerequisite material, which is just if I have a Maxwellian distribution, just an isotropic distribution, and suppose I were interested in a sound wave, well, certain parts of the sound wave, the density goes down, certain parts of the sound wave, the density goes up, and you can ask, what does the distribution function of the particles do in different parts of the wave? And if the gas is magnetized, the distribution function is going to be stretched in different directions based on whether it's in a region where the density goes down or density goes up. It's all because of these invariants. So if these sort of distortions in the distribution function surpass certain thresholds, there's kinetic instabilities that come in. And so I'm just going to show you what happens when you propagate a sound wave in a plasma. It makes the distribution function look like this, surpasses these thresholds, and then you have a mess of plasma physics that you really wish weren't there, even for a small amplitude sound wave. Right. So this is just a very simple kinetic calculation. I just have a sound wave, which in plasma is called an ionacoustic wave. And this is just the amplitude of that density versus time, and the thing kind of oscillates and it decays. So this just is showing the linear result that I showed on the first slide, which is just a sound wave exponentially damps due to Landau damping. If you turn up the amplitude of this sound wave, I mean, this is small, right? It's a 1% sound wave. If I turn it up to 10%, it stops Landau damping. And the reason why is I'm actually comparing this amplitude to 1 over the plasma beta, which in the simulation is 100. And so what's going on is that when this wave oscillates, it distorts the distribution function. Those distortions drive the system unstable. This is just, you don't actually have to know what this is. The point is that these are the distortions and they're not zero. And here's these 2 lines right here. So the fact that these distortions cross these lines just means the plasma is unstable. Now I'll actually show you just a movie of that so it's not as confusing. Right, so here's the movie. Here's just a sound wave. It's done in a box such that it's a standing sound wave, so the thing just should go up and down and just decay. This is just quantifying those departures from equilibrium. So 0 is just a Maxwellian thermodynamic equilibrium plasma, and these are these thresholds. And so this is what happens. You generate departures, you cross these thresholds, and what happens is these departures get slammed back down into these instability thresholds. I'll show that again. Like that. So something is keeping the distribution function close to a Maxwellian, and it's that process which is going to let this wave propagate when it shouldn't have. So I'll show you on the next slide the same kind of thing. But down here, these are just 3 panels of magnetic field fluctuations. So if I send a sound wave into a plasma, there's no magnetic field fluctuations. But if I send it into a weakly collisional plasma that is unstable, this is what will happen. Right. So now if you're a particle and you're trying to leach energy out of a wave by Landau damping, now you've got to navigate through all of this crud, right? And you can imagine a particle just executing Larmor motion, but then it's got all this Larmor scale junk that it has to get through, and you can't have Landau damping in a plasma like this. So just ignore that. This is a space-time diagram of what's going on. So this is the space in the box. This is time. It's a space-time diagram. The color here is the collisionality. So what I mean by that is not particle-particle collisions. This is a collisionless calculation. This is the rate at which a particle scatters off of one of those magnetic bubbles. And what you see is that as time goes and the wave propagates, all of a sudden there's a burst of collisions. And you can look at various particle trajectories that go through different portions of this. And there's just some data at the bottom of the slide, which basically says that as these particles go, they might get stuck in one of those magnetic mirrors and just bobble back and forth. They might bobble for a little bit of time and then get kicked out, go through this patch of collisional scattering, bobble down here and get kicked out. I mean, this is not a collisionless plasma. In a collisionless plasma, the particles they're just lines on this plot. Here's another particle that comes in here. It hits this batch, scatters, gets trapped in a little magnetic mirror for a while, comes back out. This one gets trapped down here in a little magnetic mirror for a while. So the point is that just the ability of the particles to free stream and thereby phase mix the distribution and dissipate things like sound waves gets interrupted because this wave distorts the distribution function in a way that the plasma just erupts into all this sort of small-scale scattering sites. You can play similar games with Alfvén waves. I don't know how much time I have, but I could show a movie of just an Alfvén wave getting ripped apart.
Show the movie.
I'll show the movie. Okay.
We always
Okay.
have time for a movie.
You can play a similar game with magnetic reconnection. So if I have, say, 2 oppositely oriented magnetic field lines and I bring them closer together, well, you're changing the field strength when you do that. And the system's not going to be Maxwellian, and then it'll go unstable to all these small-scale things, and then you can ask, how does that impact reconnection? So we haven't posted it yet. We just submitted it because it might be wrong, so we're not going to post it until it's accepted. I just showed you a single wave. I like this quote from a Nabokov novel, "The breaking of a wave cannot explain the whole sea." And of course, a turbulent plasma, which is ultimately what you want to do, but you can't fit into a little lunch seminar, may or may not be composed of a whole bunch of these waves. So Elliot and Quadrat and I are looking for a postdoc joint between Princeton and Berkeley right now to examine this kind of physics. where the microscales feed back on the large-scale waves in the context of kinetic turbulence in weak inclusional high beta plasmas. And because this is astronomy department, what I mean here is radiatively efficient accretion flows and intracluster medium and things like this, and also how these instabilities impact cosmic ray propagation. So that's all I wanted to say. Ramesh wants to see a movie. Yeah, all right. So here's, well, it's not moving yet. It's going to be a movie. There's a magnetic field this way, right there. And what you're seeing in color is just the out-of-plane magnetic field fluctuation. So in an Alfvén wave, this thing should just oscillate up and down and just travel this way. And what happens is if the amplitude of this Alfvén wave is above this threshold, 1 over the plasma beta to the 1/2, this is what happens. So all this stuff are those instabilities. And you see that Alfvén wave is just slowing down. By the way, it should have crossed the box about 2 times by now. And if I don't have it, but if I have this longer movie that my collaborator Jono has, it just basically comes to a halt and then just decays. Even though this Alfvén wave should have crossed the box multiple times. And it's just because it excites all this small scale magnetic field fluctuations that basically gives the plasma viscosity, which just damps the Alfvén wave. So that's it.
A single surfer
surfing
on a wave, then the surfer can take a lot of energy. It's insane.
Right.
If you have too many surfers, they collide with each other, and then basically you lose the ability of extracting energy.
Yeah, or if you're surfing a wave in a storm, if there's a wave that has a bunch of other waves on top of it, you're going to have a hard time staying on the big wave. Yeah.
Now, shock waves are therefore safe, right?
Yeah.
They're very strong, and they will behave just like in collisional plasma.
Right.
So what I understood from what you said is, if the field is fairly strong, then you have to screen in order to propagate the signal. Very low amplitude waves cannot propagate. But as you make the field weaker and weaker, even whispers can get through. That's the scaling, right? The delta over 1 over.
Right.
So you can go to really weak fields and you can propagate all sorts of waves. But zero field is a different story.
Yeah.
Is that correct?
Right.
So that is a singular limit.
Yeah.
So you go to zero field, and then suddenly you're back to Landau damping,
Yeah.
and nothing propagates.
Yeah. Yeah, the role of the magnetic field is just to have a direction. It just needs to say this is the right way to go.
No, but I could also imagine a turbulent, isotropically turbulent, weak field. I would just use the Chu-Goldberger scalings, and presumably it'll propagate waves. Will it not?
Yeah.
Until the field goes to zero.
Yeah.
Other questions? Eric?
So in this theory of turbulent reconnection, the turbulent waves are supposed to increase the speed of the reconnection, and this doesn't sound like good news for that idea.
It turns out to be good news, which is in this paper, in the sense that the reason this turbulent reconnection works is that you've got 2 current sheets, and if they're turbulent, you're basically creating a whole bunch of small current sheets with this turbulence, and you're sort of exciting the reconnection process. These instabilities will also create small-scale distortions in the magnetic field, just like turbulence does, and they'll sort of excite reconnection because you're sort of spurring on the tearing modes that rip apart the reconnecting layer.
Yeah, I was thinking more of you need these larger scale turbulent waves increase
To mix the field lines. Oh, okay.
And so this would say these waves would be damped out. But
Oh, I see what you're saying. Well, I think the more interesting application here is we know that cosmic rays diffuse because they scatter off of Alfvén waves that they excite. But if there's some kind of limit on the size of the Alfvén wave that they can excite, maybe the diffusion of the cosmic rays will change. But anyway.
Thank you very much.
Yeah. Okay, thank you. You're being bugged soon.
I'm being bugged. Thanks very much. Right, a movie especially to put you off your lunch. So this is just a brief introduction to some follow-up work we've been doing on possible applications of astrometry, in particular for a long-established concept of using astrometry to detect gravitational waves. It was first proposed decades ago, back in the 80s, and was part of the original science case for Gaia. But it hadn't been followed up very much, and so we looked at just what you could actually do. The key name here, let me show you, is my student Dan Mihailov, who finishes next week, and he's visiting here at the end of the month, so he can go through more of this in detail. But anyway, that's just a simulation of what an ordinary Einstein gravity wave would do for a single stable phase gravitational wave coming through the North Pole. This would correspond to a supermassive black hole binary in the last 10,000 years or something before its merger. And so it would give it effectively constant frequency map across the sky. And this would be visible in this dipole astrometric residuals once you've taken out all the proper motions and everything of all the stars. So that's a prediction from long ago. The interesting thing is then say, well, how does it correspond to something that's astrophysically interesting? And so on the left-hand side here, I've got a standard strain versus frequency diagram for gravity waves. So down here are the ground-based systems, the low-mass binaries, and you move up in mass as you go across. This is the future space systems. And in here is the region we are with the pulsar timing arrays and Gaia. And so zooming in on this situation here and trying to simulate how accurately one can measure the real gravitational waves, these are the results here. So the different colours are the current results from the different pulsar timing arrays, and the black is Gaia. And so the interesting thing is that they're comparable, and so one could use them as a verification process. The gravitational wave background is down about here somewhere, and Gaia loses that just because the mission's not long enough. But up at this end, this is where the majority of the signal should be, and so this is potentially interesting region. These are the sort of 5 times 10 to the 8, 10 to the 9 solar mass type black hole binaries are in here. These are huge things up here. So this is potentially interesting, and there may be something in it. However, the thing we've done is to go on beyond that and say, well, can you do more than just confirm the pulsar timing array? And the interesting issue there is to say, well, what sort of polarization properties are possible from gravitational waves and what sort of patterns? And as you probably all know, the standard TT tensor tells you that the standard GR gives you these plus and cross polarizations, and there they are there. But 4 other types are possible as well. You can have scalar or the longitudinal polarizations for other theories of gravity. Only these 2 in GR. But all these others are possible, and this is what they look like. And so it's interesting to say, could one in principle, even with the pulsar timing, find these things and say something about alternative gravity theories? And so we had a look at that. Here's another, these are the GR polarizations this time rather than signal. And so, but the interesting thing is not so much what does that pattern look like. You obviously could hope to tell the difference between that and the one I gave you before. But to say, okay, well, what are the correlations? And so there is a famous thing called the Hellingsdown curves, date back from the 80s, which is this dotted line here, which is the correlation between different pulsars across the sky. So this is a correlation function for the pulsar timing arrays. And we it has been known for a while that there must be something similar for astrometric polarizations. And so it turns out all of the astrometric stuff from this point on, that I'm going to mention, turns out to be analytic. The equations are very long, but they're all analytic. And so this is the equivalent of Helling Downs for astrometry. And so that's new. And this red one here is the cross, that's also new, is the cross correlation. So it's the cross polarization, correlation function for both astrometric and PTA, so redshift detections. And so this signal here is what one would hope to look for by using the combination of the two astrometric and redshift PTA timing. This, in fact, is generalized. One can generalize it straightforwardly to look at a background signal rather than from a single source. It's particularly at lower frequencies. It's a good thing you finished eating. This is what the sky would look like from a background system of non-GR radiation. So you can see it tipping up and down. You can see this is obviously not just simple quadrupole. It turns out you can actually calculate all the correlations, again, all analytically except one, between these things. And so you get all these correlation functions for all of the different types of polarization that are possible. And so these are the cross-correlation functions between the PTA redshifts and the astrometric. And you can see there is actually quite a significant difference in the different systems. So in principle, one could turn this stuff around and say, what is the signal? What is the result from the redshift astrometry correlations? And that is really what I want to say. That is the result that, in principle, one can impose on data and actually look for all of this stuff, is all of these things are new. One point I should probably have made, because you'll just ask about it anyway, is, is why is there this difference between the Hellingsdown amplitude and the astrometric amplitude? And this is the difference that made it possible to do all these things analytically. And the pulsar timing system, you have to do it maximally. You have to fit the distances to each pulsar while you're doing the redshift. But for astrometry, everything is in the distance source limit. And this completely simplifies everything. But if you keep the full distribution in, you can do it. But that gives you this extra amplitude and therefore the extra sensitivity. And so in principle, this also gives you sufficient sensitivity to test the graviton mass. I haven't got the slides here. Diane will show you them in a month. But you can do similar things to this, one analytic and one numerical, depending on whether the velocity of the gravitational wave is less than or greater than the speed of light. And again, they're surprisingly, interestingly different, even given the existing limits on where we are. The last point, which you'll probably ask about, is are you going to see anything in here? And the answer is probably no. The simulations of what is actually in the sky are not good, of course. And as we know, LIGO was just lucky. It found something that no one predicted. But new surveys always find something bright that no one predicted. And so maybe there is something there. It turns out if there is a binary black hole of 2 10 to the 9th solar mass black holes waiting to merge somewhere in coma or closer, then it will come in about here, and so you'll see it. But if there isn't, you won't. The predictions are down about another order of magnitude still to go. But down here, there should be a lot more black holes at those sorts of masses, and so maybe something there will be visible. That's all I want to say. Thank you. Well, yeah, you know the gravity is about 10 to minus 17 or something. So that signal is interesting. You can still do significantly better. For the polarizations, there's very little been done actually on alternatives. I think the PTA people could in principle, but these calculations of the new, where'd they go? This. These have not been done in a straightforward, robust way before. People have done all sorts of numerical approximations to it, but nobody's ever done it. And so I've never seen anybody actually trying to impose these on the PTA data and get it straight. Oh, LIGO, yeah.
Does LIGO shed any light on set constraints?
Yep.
Because you can easily run it through their detector orientation and so on and ask, would they see something from different waves of the signal?
Yes, they are doing that test now. Was it Max Easy who was here the other day?
Yeah,
Somebody from one of the Einstein Fellows who's now working at MIT. It's really, to my mind, surprisingly powerful. I think they have one paper already on one event and new work which will soon be out where they've tried not to do not exactly what you've done, and this is absolutely fascinating and obviously not covered by what they've done, but they have checked to see whether the polarization measurements are consistent with or in contradiction to Einstein's theory, and they can rule out the ones for the merging black holes that are inconsistent with Einstein's theory. And this is only going to get better as they have more and more results.
Yes, just taking it off, but you can do these same experiments right across the entire spectrum, of course. It's just gravity, so any where you have a signal is good enough.
Questions? Dan and then
Sure. I'm up here. Could you just mention quickly if Gaia were to take data for 9 years, how much better would that go?
Yeah, where is it? This one. Yeah, Gaia will, under present terms, operate for 10.5 years, subject to spacecraft not failing and a little bit of money being found. And that will push it back here, back it down here by a factor of 3, which isn't much. It only brings you back to about here. So that's useful, but not much. There's another potential order of magnitude gain back down this way, which you can't get from pulsar timing because they glitch and so on. The years get in the way. 6 months a year sampling and so on. So this is short period stuff, and that's done. But yeah, you can potentially go another factor 2 there. I mean, really, in a fundamental sense, this is a case for doing another Gaia.
Yeah, it's the same problem. I mean, I was shocked to see that Gaia is actually more sensitive than nanograph.
So were we, actually.
Already at this
really
point.
Didn't believe that was going to come out.
Yeah. so tell me about the other two guys. What is EPTA and PPTA?
These are 3 different subsets of pulsar timing arrays in which we put them all together. So this is the pulsar timing array. This is the putting everything together, these two. And this is a smaller subset of the data.
But this is all today's?
This is all literature data, yeah, that's
Okay,
right. So these are all working systems. The SKA pulsar timing will eventually get further down and maybe they'll actually detect something, but these are actually operating systems today.
for more information about Gaia, please come to the CFA program at 4 p.m. Thank you.
Can someone? Hey, sorry. This doesn't work with HDMI, so I need an HDMI connector. He gave it to me when I tested it earlier, but I just don't know.
You just can find it here.
Yeah, well, he gave it to me. Oh, there it is. Okay. All right. Thank you.
sorry about this. Hello, my name is Rana Ezzedine. Oh. Okay. So my name is Rana Ezzedine. I'm a postdoc at MIT, and I want to talk to you a little bit about my research on the oldest stars in the galaxy. So I'm going to start first by telling you why we're interested to study these very, very iron-poor stars or very old stars. They are, so we don't have any observational evidence that we have first stars around. They must have been very massive and died right away. But we do have evidence that we have the next best thing, which is the metal-poor stars that are low-massed and are probably long-lived till today. And the reason is why we think they're still around for today is because they have very little metals in their atmospheres, which shows that they must have been enriched by at most 1 or 2 supernova events into their atmospheres. And these are the type of stars that we can use to do stellar archaeology, which is basically use these stellar relics to understand the first stars observationally. And when I say that these are metal-poor stars, I don't mean that they are periodic. I don't mean that they have little metals from the periodic table, but what I mean by metals is basically the astronomers' metals, which is everything that is heavier than hydrogen and helium. These types of stars have been over the years by multiple reviews classified into several categories, starting from metal-poor stars, which is basically the total iron to hydrogen abundance below -1, and until whatever ridiculous name you want to give them. However, we have not discovered any star below -10. The lowest metallicity or the lowest iron abundance star we have detected has, there are 2 stars. There's the Color star that was discovered in 2014. It has an iron abundance or metallicity upper limit below -7. And one that has been discovered by Aguado this year and has been actually followed up by Frebel et al. Our paper is now on the archive since yesterday, so you can check it out. It doesn't have any iron lines, but it has an upper limit of below -6, which is really interesting. So,
these names are actually used?
Yes, we use all of these names.
Including the last one.
Yeah.
Yes, including the last one, but we haven't used it on an actual star yet. But hopefully, fingers crossed. Yes, that's true. I will talk a little bit about this. So there is carbon, but we usually classify them from iron because that's what we do for stars, right? So how can we use these stellar relics to infer the any properties of the first stars? Since, as I said, we consider that they have been enriched by 1 supernova event from the first star, we can compare the abundance pattern of these very old or very iron-poor stars to the supernova yields, supernova explosion yields of metal-free stars. And these models, of course, they have been calculated at specific masses and at specific explosion energies. Once we have a match, we can that way build the IMF of the first stars and infer more information about these types of stars. However, there's a problem with this. And this is what I want to talk about. When we determine abundances, you would think, well, that's fine. We have a spectrum. We just measure the abundances. Abundances are not measurable quantities. They are modeled. And you can see this in this comic by Ben Gustafsson from Uppsala, who shows you the way we do it. There's a lot of atomic physics, a lot of modeling that goes before we can actually determine an abundance of a star. The idea is that we want to finally compare the observed spectrum to a synthetic spectrum. However, what goes into the synthetic spectrum is a lot of assumptions that astronomers use to make their lives easier. One of these assumptions, I'm not going to talk about all of them because that will take a lot of time, but one of them I want to talk about today is the assumption of local thermodynamic equilibrium, or as we call it, LTE. So what is LTE? It's basically assuming that in the stellar photosphere, the matter is in equilibrium, which means that we can define the populations of the levels that are found, of the atoms that are found in the atmosphere, only as a function of temperature or pressure, and this can be done along all the stratification inside the atmosphere of the star. Now, as you can imagine, this is doable if we have enough collisions to induce this equilibrium in the atmosphere of the star. But this is not the case, for example, for stars that have extended atmospheres like giants or supergiants, but also metal-poor stars, because they don't have enough metals in their atmospheres to induce this equilibrium. In this case, what has to be done is do a non-LTE, which is the opposite of LTE analysis. What this means is actually that, considering that if we have a transition from which we see an absorption line in a metal-poor star, this transition has been affected by so many other transitions inside the atom, inside the atmosphere. So what we have to consider is that our photons carry non-local information. Let me paint a nicer picture to you than this. For example, in LTE, if we want to study one absorption line, what we have to do is include all the atomic data for one transition. If we want to do this in non-LTE, we have to consider for a certain element that we're studying the full atom and all the energy levels that are there, and then include all possible transitions. And this is just radiative transitions. There's also collisional transitions. Of course, this is a lot of work that took me all of my PhD to do. However, it's important, and I will show you why. This is, for the previous example was for iron 1, and this is for iron 2. It's also even more transitions. So it's a lot. This is important, and now I will start to show you why. Here I show how do we quantify this departure from LTE, or how do we quantify how important is non-LTE? By introducing a departure coefficient, which is basically the ratio of the level populations calculated in non-LTE over those in LTE. And here I show the case for three stars, the Sun, and 2 ultra-metal-poor stars with very low iron abundances. As you can see, and this is the departure coefficient as a function of optical depth inside the atmosphere. So this is going outside the atmosphere of the star. You can see that for the very metal-poor stars, the departure coefficient can be pretty deep and can be important. Now, let's look at how this affects our measurements that we use in astrophysical problems. For example, the temperature, the gravity. So usually we use iron lines to determine spectroscopically the stellar parameters of the star. And if we use LTE, we can actually underestimate a lot of these parameters. Here I show the difference between non-LTE and LTE, for example, in effective temperature, gravity, microturbulence, and metallicity. And this is all color-coded as a function of lower metallicities, and I've tested this over 20 standard halo metal-poor stars. You can see that the deviations from LTE become larger, up to 500 Kelvin for the very metal-poor star at minus 3.6. Similarly, for the gravity, we can underestimate in LTE the gravity by 1.2 dex, also for the microturbulent velocity, but also for the metallicity and the iron abundance, which we use it as an input for all of our subsequent studies. Now, you might ask me, okay, well, this is 0.5 dex. What if we go lower in metallicity? What happens? Does this stop? Do these corrections stop? Not really. They keep going up. And this is a study that we did in 2017 for stars below -4. So this is the 20 known most iron-poor stars from the literature. And we found out that the corrections can get up to 1 dex for the Keller star, which is the most iron-poor star known. But interestingly, what we found is that these corrections as a function of metallicity have some kind of linear trend, and we came up with this equation that can be applied to. So if you have an LTE metallicity, you can apply this equation to determine your correction. But nice enough, we found that this linear relation also applies to the less metal-poor stars without even having to enforce it, which is nice. But what about other elements? So we found that there's a correlation in terms of the corrections for iron. What about other elements like magnesium and calcium? We find that the corrections are a little bit less, but they are significant nonetheless. 0.5 dex is not a small number. Similarly for calcium, and this is work in preparation right now. One thing that we know, or how do we know that non-LTE works, or it's that the physics actually works? Usually, when we have one element in an atmosphere of the star, if we have it in two ionization stages, let's say calcium 1 and calcium 2, we are supposed to get the same abundances from both these ionization species without enforcing them. And here I show an example for these very model poor stars below -4 as a function of temperature. I show the difference between abundances determined from calcium 1 and calcium 2. You can see that the abundances are very well in agreement with each other in non-LTE, while in LTE we have this huge spread, which means that even at this extreme low end of the metallicity, non-LTE works, which means that it also works for the case of even less metal poor stars. I will leave here my takeaway points of this study. Abundances are not measured, they are determined, and models are important. Non-LTE can be very important for metal poor stars, especially when we want to infer information about the first stars. They can underestimate the values that we use in astrophysical problems up to these values, so it's important to do them. It takes a lot of work. You don't have to do it. I'm happy to do the work for you, so if you're interested, talk to me after. Thank you. Thank you.
One thing I want to suggest, instead of calling the metal poor, it should be iron poor, or if you want to be brief, anemic star. Because actually, most of them have a lot of carbon. So the model that people have in mind for making them, the most popular one is you have a massive star that was supposed to go supernova, but the iron core implodes and ends up in the black hole. So you don't get the iron out, but you get the outer layers of the envelope out. So carbon gets enriched, but not the iron. So
that's right.
These are just anemic stars.
That's right, I agree, and I would talk to the people who write the reviews about this. That's true that most of the metal poor stars are actually called carbon-enhanced metal poor stars. However, we have found, yes, I know, but we have found some stars that are not carbon-enhanced, but at the same time metal poor stars. So there are so many subcategories that we could go into these, but at least these very old ones, they are all more or less carbon-enhanced. So yes, I agree.
That you derive for correcting for non-LTE effect. Does this work for any measurement of iron, or does it have to be done in particular spectral region?
So these stars are all studied in the optical region. Of course, they don't have a lot of line because they are metal poor. So basically, yeah, it can be applied, I think, to different regions of the spectrum. I have recently applied it for some UV lines, and it works okay. So it shouldn't be that different. What should be different is depending where the line forms in the atmosphere, right? But most of the lines form more or less in the same region, so the non-LTE effects should behave the same.
So let's thank Rana and all.
It was great to see you do this with so much energy.
Thank you.
Fantastic results.
Thank you so much.
So in terms of what it's telling us, though, so does that mean that the metal poor stars that we see are actually less metal poor than we think they are?
Yes, exactly.
That's a disappointing result.
It is. I mean, depending on the relative scale, they're still metal poor, but not as metal poor as we thought they were.
Right.
Yeah.
So we have to do better with the observations.
I guess so, yeah.
No, beautiful work.
Thank you very much.
Very nice to meet you.
Thank you very much. Thank you.
Hi.
Hi.
I'm Anna Bonazza.
Hi. Very nice to meet you.
Yeah, I really like your work.
Thank you.
We heard a lot about it from Anna. I think last year she gave a colloquium, and then you were like very much featured there. So it's like great to hear from you directly.
Thank you, and your work too. I've seen some work about Gaia. I was actually talking earlier to Sergi Blanco Quaresma, and it should be. I think it would be interesting to implement these stuff, corrections. And I know a lot of people are doing it, but a lot of people also are like, well, I don't care about them that much. So I like to show that no, this is important.
One of my collaborators like to. I think you would show your plot like show of force when you just have like one transition, then like 80,000.
Yes.
Yeah, Yeah, that's pretty amazing. And are they all like equally? Are some maybe more kind of forbidden transitions, or are they actually everything needs to be taken into account?
Some of them are, but like forbidden transition means that it doesn't have a strong transition probability, right? So they are usually not used a lot in the abundance analysis. So mostly it's the strongest line, at least in these stars, because we can find, even they're very small and such type of stars. But yeah, you can find it. The corrections, as I said, depend on where it's formed inside the atmosphere, so they can differ. But usually we find that most of them have strong lines also.
And it's like the naive picture is that there's less ions or so, like in middle of course, so there's like less kind of, and then that's kind of why they can travel longer and will scatter.
Yes, that's the reason why they have it. Thank you very much.
Certainly, thank you.
Are you staying around for today?